once you open a proton NMR, it should look something like this. And one of the first things you want to do is to zoom into the area that where you think you should have the residual solvent peak. That is, if you use chloroform, deuterated chloroform, there's always bound to be a little bit of undeuteраted chloroform molecule in the mix, a small amount, and that's going to be the residual solvent, and that's going to be true no matter what deuterated solvent you use. It's never going to be 100%. In this case, I should have chloroform peak around 7.26. Oh, this is kind of a badly shimmed spectrum, so sorry, it's not a good example to be showing you because this chloroform peak is not very symmetrical, but oh well. What you want to do is once you zoom in using this zoom in tool right here, you want to use the reference tool and then highlight the chloroform peak or whatever the solvent peak is, and then go to solvent, click on chloroform and hit OK, and what that does is it will shift the spectrum so that this peak is exactly at the position that chloroform is supposed to appear, so that this chemical shift is calibrated against this chloroform peak. And if I zoom out, by the way, you can use the scroll button to make this big or small or what have you. And what you do next is to zoom into so that you can look at individual peaks well. And what you want to do is to both do peak picking and integration. For peak picking, I would use the manual threshold tool, and if I cover the top of all the peaks like so, I want you to notice it automatically picked all the peaks. And if you go to integration manual tool, I can integrate each of these peaks by dragging the mouse like so. Okay. And so what that does is it integrated the area under each of these peaks. This peak here, there's really two signals, but since they're kind of overlapped, so I'm just going to integrate both of these at the same time. I'm not going to integrate this peak because that's the chloroform solvent peak, so it doesn't really matter. Hopefully you can kind of tell that the ratio of the integration is 1 to 1 to 1 to 2. That's reflected in the numbers here at the bottom, more quantitatively. What you want to do at this point is you can right click on any of these peaks that you think you have a pretty good guess as to how many protons it's worth, and then click on edit integral. That will bring up this integration manager, and you can adjust the number of protons that you think that peak is worth. It might be just one hydrogen, but if you have a reason to believe that that particular peak is a methyl group, for instance, then you can increase this to 3 hydrogens. Alternatively, what you can do is, if you're pretty confident about the chemical formula of this molecule, you can adjust the total number of hydrogens to be the number of hydrogens of this molecule. Now, when you do so, you do need to be careful because often the protons on a heteroatom, so that would be like alcohol or amine, those protons often do not show up in proton NMR. And so you might need to subtract heteroatom hydrogen counts from the total numbers. If you know the total number of hydrogen, like let's say it's supposed to be 5, then that will be reflected in the integration here. So what I did is I set that to be 5, and those 5 protons are distributed among these 4 integrations I did. So it's still roughly 1 to 1 to 1 to 2, but it's a little bit different set of numbers. depending on the exact integration for each peak. So hopefully that makes sense. And sometimes you have a pretty clear splitting pattern, like let's say, let's look in here. Like this is a fairly clear doublet. So for that reason, if I do peak pick, I want you to know that you should report that the actual signal is between the middle of these two signals, okay? So this would be this right here, to 3.25 is the actual location of the signal. It's a doublet that's split by this much, and if you use this cursor tool, you can calculate the coupling constant that this doublet is split up by. So it's split up by, it says 14 hertz, okay, or 13.98, 14 hertz is the coupling constant for this doublet. And then of course you could do the integration and whatnot. And once you have all that information, you could click on the report peaks, and that'll report the location of all the peaks, and if there's any integration information, that would be reflected in this integral table. That this peak is worth 1 hydrogen, that peak is worth 1 hydrogen, 2, and maybe this one being 4, and so forth. Okay. Once you print out your NMR spectrum, please make sure, don't forget to paste that into your notebook. Okay.